Welcome to Brain Vision.
We have a problem here that's going through the forces on a charged particle due to magnetic fields, as well as electric fields. So we have a proton that's in a magnetic field, and we know its initial velocity, which is given in this here box on the right here. And for the first part of the problem, all we want to do is find out what is the force on this particle due to the magnetic field. So to do this, we can use this here equation. F is equal to Q V cross B. So this is just force on a charged particle due to magnetic field. So we can plug in what we know here, right? So velocity is this. So as 1.5 times 10 to the 5th meters per second in the x direction. It has 0 in the y direction, so we'll just drop that term. And then in the z direction, 2 times 10 to the 5th times our k hat unit vector. And that'll be crossed with the magnetic field, which is 0.5 teslas in the I direction. So expanding this out, we see here this first term ends up dropping out because we know that I cross I is equal to 0, since the cross product of a vector with itself is equal to 0. And so this ends up being Q, 2 times 10 to the 5th times 0.5 times the vector k cross I. Now this here, we can just solve using right-hand rule quite simply, and what we would find is that this unit vector is equal to j hat. So we get this, 0.5 in the j hat direction. So all we have to do now is just plug this into our calculator, plug in the charge of a proton, and what we end up with is that the magnitude of our force is 1.6 times 10 to the negative 14 in newtons, and that force is pointing in the y direction, at least at this time, t equals 0. Okay, so now for part B, what we're going to do is we're adding in an electric field, right? So that electric field is equal to this. It has a magnitude of 2 times 10 to the 4th volts per meter, and is pointed in the x direction. What this problem asks us is, will the proton have some acceleration in the x direction? And the answer is, of course, yes. Simply because the force on the particle due to the magnetic field has no component in the x direction, but we of course know that the force due to the electric field, which I'll just denote by subscript E, is equal to QE, right? That's the full force due to the electric field, and the electric field, of course, points in the x direction, and so there will be some acceleration in the x direction. Which now brings us to part C, which asks us to describe the motion. Now, so we know from part B that there's going to be some acceleration in the x direction. So the particle will be drifting in that direction. And we also know that particles in a magnetic field tend to rotate in circles, right? So in this case, it will be a sort of helical shape. It's going to be like this, right? Where the direction that it's moving in will be the x direction, I hat, and the direction that it's sort of rotating in is going to be the yz plane. And now the question also asks us, will the radius of our orbit be affected by this acceleration? And the answer is no, it won't. Why? Well, because the velocity in the x direction does not affect the force due to the magnetic field. So FB, right? Because FB, or our magnetic field, points in the x direction, the x component of the velocity doesn't actually affect the magnetic force at all. And so the radius of our orbit will not change. This brings us to our last problem. So part D. Part D asks us to find what the displacement of our particle is in the x direction. And the time that they asked us to do this at is the period of the orbit divided by 2. And so this part of the problem has kind of two parts to it. The first one is to find what the period is, and then the second part is to find the displacement in the x direction, delta x. So let's start off by finding the period. So to do this, we can just look at our force, FB. So we calculated what the force is, right? The magnitude of it is 1.6 times 10 to the negative 14 newtons. However, we know that this causes the particle to move in a circular direction, right? And so this is actually a centripetal force. So it's also equal to mv squared over r, right? Because that's what centripetal force is. Now, what we will want to do is express this in terms of the period in order to get the period. So to do this, what we can do is we can cleverly express the velocity in terms of that, right? So the velocity, we know, so this velocity, as it turns out, is actually the velocity in the yz direction. It's not the full magnitude of the velocity, it's just vy squared plus vz squared square root, right? And the reason for this is because that's the velocity ignoring the x direction. So, right, since that's the direction in which the particle is rotating in. And so that component of the velocity we can express like this. It's the circumference of its orbit, 2 pi r, divided by its period, since we know that the particle is going to go a distance 2 pi r every t seconds, right? And so we can use this equation to solve for r. And so what we would find is that r is equal to velocity times the period divided by 2 pi. Okay, so now we can take this and just substitute it into here. And what we end up with here now, after some simplification, is 2 pi mv over the period. All right, now we can just solve for what t is. So t would be 2 pi mv over the magnetic force, 1.6 times 10 to the negative 14 newtons. Now here, right, we still need the velocity, but the velocity expressed up here, it's this square root of these two terms squared. However, the point at which we picked this, we know that Vy is actually equal to 0. And so this is actually just equal to the z component. And so we just plug the z component into this part of the problem, and we can get the period straight out. So this is 1.3 times 10 to the negative 7 seconds. That is the period of our orbit. So now we need to do the next part, which is to find the displacement. So to do this, we are going to use some kinematics, and I'll show you why. Right? So the force on the particle in the x direction is simply going to be the charge of the particle times the electric field. The reason being is that there's no component of the force due to the magnetic field in this direction, right? So it's all QE. Now that is equal to MA in the x direction. And so we could use this to find what the acceleration in the x direction is. And that'll just be QE over the mass And we can get a number out of this. It's 1.92 times 10 to the 12 meters per second squared. Now that is just a constant number, right? And since that tells us that the acceleration is constant throughout its motion, we can use kinematics. So the kinematic equation for position, or in this case displacement, delta x, is going to be 1/2 acceleration times time squared plus our initial velocity times time. Now the initial velocity, we're actually also given in the problem, right? That's just the x component, which is 1.5 times 10 to the 5th meters per second. And then the time that we're interested in is the period over 2. And so if we plug in our numbers here, we would get the displacement straight out, and we would find that this is equal to 0.0138 in terms of meters, or we can also express this in terms of centimeters to make more sense of it, which is 1.4.